Hello, in this video we'll try to learn rational functions. So let us see. Let's say I have a function of x, and function of x is going to have a denominator and numerator. So let's say I represent the numerator using a function nx, and I represent the denominator using a function called dx. So in this case both nx and dx are both polynomial. Okay, so they can be both polynomial function. Okay, so both are polynomial function. All right, so that is a simple definition. All right, so now let us see some example of polynomial function. All right, so let's say I have one polynomial function which is function of x equals 3x square minus 12 over x minus 1. This is my first polynomial function, and let's say I have another polynomial function which is gx equals x over x square minus 6x plus 8. And finally let's say I have another polynomial function which is rational function hx equals x square minus 4 over x minus 2. So these are my three rational function. So first of all I will try to find the domain of each rational function. Okay, so that is my objective, finding domain. Right, so we want to find a domain. Now we know that the definition of domain is basically the values of x for which the function is defined. Okay, now let us look at the denominator here. So denominator of this rational function which is x minus 1. Now whatever is inside this box cannot be equal to 0, because if it is equal to 0 then I am going to have basically a denominator 0, and denominator 0 means I cannot evaluate the function. So that means and what is the inside? It is x minus 1. So I can say x minus 1 cannot be equal to 0, so x cannot be equal to 1. So this is essentially the denominator in this way of writing. Now if I want to write down in proper mathematical notation, that will be a negative infinite to 1 and then union 1 to positive infinite. Okay, so this is the domain for this particular function. Okay, so this is the number 1. So now let us look at my second problem. So for my second problem, as you can see, I have basically a denominator. So I'll try to factor the denominator. So I have x square minus 6x plus 8. So if I factor it, I am going to get x minus 4 and then x minus 2. So these are my two factor. All right, so now as before we know that my denominator cannot be equal to 0, so I can say that this denominator cannot be equal to 0. So that means this cannot be equal to 0. So what is inside? Inside we know it is x minus 4 multiplied by x minus 2 cannot be 0. So individually I can say x minus 4 cannot be equal to 0, and or x minus 2 also cannot be equal to 0. So I can write x cannot be equal to 4, and here I can say x cannot be equal to 2. So these are basically my the domain in this way of writing. Now of course, if I want to write down in a proper mathematical notation, so it will be a negative infinite to 2 union 2 to 4 and union 4 to infinite. Okay, so this is the domain for my this particular function, right? So now let us look at the third function. Of course, third function the same way I can say x minus 2 cannot be equal to 0. So I can say x minus 2 cannot be equal to 0. So x cannot be equal to 2. So this is essentially my domain, but if I write down in that notation, so negative infinite to 2 and union 2 to positive infinite. All right, so this is basically how we find a domain of any rational function. All right, so now I am going to show you a interesting fact in rational function, which is vertical asymptote. All right, so let us see what is vertical asymptote. So we are going to try to learn vertical asymptote. Okay, so before I show you any type of derivation or any type of equation, I want to first want you to see a example function that I'm going to try to plot. So I'm going to try to plot, let's say, a function of x is 1 over x minus 1. Okay, so I'll try to plot this function. Okay, now where I'm going to try to plot, I'm going to try to plot it over here. All right, so for now I'm going to try to basically draw a line here, vertical line. So don't bother it now why I'm drawing, you are going to learn it just now. Okay, so let's say this line is at x equal to 1. Okay, at x equal to 1 I draw a vertical line. Okay, so first of all, let's see, I'm going to use a point method. So if x equals negative 1, what is my function of negative 1? Function of negative 1 is 1 over x is negative 1, and I have another negative 1 which is negative 0.5. Okay, so x is negative 1, y is 0.5, which is x is negative 1, y is so this is somewhere here. Okay, now let's see, if x is equal to 0, what is my function of 0? It is 1 over 0 minus 1, so which is negative 1. So 0 negative 1 is somewhere here. Okay, so if x is equal to let's say 0.9, what I get? Function of 0.9 equals 1 over 0.9 minus 1, which is 1 over negative 0.1, which is what? Negative 10. Okay, so negative 10 is somewhere here. So this is 0.91. Okay, so similarly, if x is 0.99, very close to x equal to 1, so what is my function of 0.99, which is equals 1 over 0.99 minus 1, which is 1 over negative 0.01, which is negative 100. So which even goes beyond actually my so if you notice actually my graph is never going to cross that x equal to 1 line, because at x equal to 1 my function is not defined, because x cannot be equal to 1. So now if I draw this portion of my graph, what I get, I basically get a graph something like that. Okay, so it is never going to touch my x equal to 1 line. Okay, so similarly if I try to put at x equal to 1.1, I got what, function of 1.1 which is equals 1 over 1.1 minus 1, which is 1 over 0.1, which is this time positive 10. So positive 10 is somewhere here, and if you plot the other point, you are going to basically find a graph something like that. So now if you notice that my plot of my graph never crosses at x equal to 1 line, and on also my both the line are asymptote with at x equal to 1. Okay, so this line, vertical line at x equal to 1 is called vertical asymptote. So this line at x equal to 1 is called vertical asymptote. Vertical asymptote. So this is actually the definition of vertical asymptote. All right, so so let's look at some other example of vertical asymptote. Let's say I have line a vertical asymptote here, and this time on the left hand side, let's say it is going upward, and on the left hand side let's say it is going downward. Okay, the opposite of the other one. And it can happen also that both in the left hand and right hand side it is going upward. So I have vertical asymptote here, I have vertical asymptote here. Okay, or it can happen that both is going downward. All right, so means there are many possibilities for vertical asymptote, as you can see. So it is going downstairs, it is going downward, and the right hand side it is also going downward. So these are some examples of the possibilities of vertical asymptote. So now let's see how we can locate a vertical asymptote. Okay, so that is the important one. So locating vertical asymptote. Alright, so let's first look at our definition of my rational function. So I have, let's say, function of x is, in the numerator I have a function, a polynomial, and on the denominator I have a polynomial dx. So to find or locate a vertical asymptote, what we are going to do, we are going to try to find the real zeros or x-intercept of dx. So what you are going to find, real zeros or x-intercept of dx. Okay, not the function of x. So to find real zeros or x-intercept of dx, what we need to do, so that means put dx equal to 0. So that is how we are going to find vertical asymptote. Okay, so let us do some example. All right, so let's say I have a function a which is function of x equals 1 over x minus 1. all right. And let's say I have a function, another function, a function of gx, which is equals 1 over x square minus 9. And let's say I have another function c, which is hx, 1 over x square plus 1. Okay, so these are my three function. So let us see for the first one. We know that what is my denominator. My denominator is x minus 1, so I need to equate what, dx, means whatever the denominator is equal to 0. All right, to find my particle asymptote. So x minus need to be equal to 0, so x equal to 1. So at x equal to 1, I am going to have a vertical asymptote. And just to show you the picture of that, remember we draw this function a little while ago. So what we found, at x equal to 1, I have a vertical asymptote. All right, so we saw it also in the example. Now let's look at the other one. Okay, so for this one, we know that the same, I need to equate my denominator. I need to equate my denominator equal to 0. So this is my denominator, and I am going to equate to 0. So let's try to solve it. So x square minus 9, so x square equal to 9, so x equals plus minus square root of 9, which is plus minus 3. So I have x equal to 3, and I have x equals negative 3. So for this problem, I have two vertical asymptote. One vertical asymptote as a vertical line at x equal to 3, another vertical asymptote at a vertical line at x equal to negative 3. So two asymptote. All right, so now let us look at my third function. So let's see my denominator. Okay, so this is my denominator. So if I equate my denominator equal to 0, so what I get? So this is x square plus 1. So what is my x square? Equals negative 1. So x is plus minus square root of negative 1, which is what? Plus minus I. Now remember what we says in the definition. We says the real zeros of the denominator. Now this is not a real number, so this is what, imaginary number. So that means for my third problem, I do not have any vertical asymptote, so no vertical asymptote. So no vertical asymptote for this particular problem. Okay, so that is basically the three example. All right, so now we are going to try to see another three example, and we'll try to plot particle asymptote this time. Okay, approximately. All right, so let's say, so I have a function hx equals x square minus 9 over x minus 3. All right, so let's plot this function first. Now first of all, I am going to try to find the domain of this function. So to find out the domain, what I need to do, I need to make sure my denominator cannot be equal to 0. So what is my domain of this function? That this denominator cannot be equal to 0. So what I get, x cannot be equal to 3. So that is my domain I need to follow. Now let's simplify. As you can see, my numerator is x square minus 9. So I can see x square minus 9 is 3 square, and denominator is x minus 3. So my numerator x square minus 3 square I can write as x plus 3 multiplied by x minus 3 over x minus 3. Okay, so this is my hx. Now as you can see, I have a two common term, which is what, x minus 3 here, x minus 3 cancel out. Now you need to remember that x cannot be equal to 3, so this is the domain. So finally what I found, I found that y equals hx equals what, x plus 3. And remember, in this function x cannot be equal to 3. So tell me, y equals x plus 3, what kind of graph it is? It is basically a straight line. So if I try to draw the straight line, so this is x, this is y. If I try to draw the straight line, it will be something like that. So this is the straight line. Now remember, x cannot be equal to 3. So x, so let's say 3x is 3 is here, so it is my 3 equal to 3. So if I go, so that means in my function this point is not included in this included in the graph. So that is, I'm going to have a little hole here. Okay, so this is basically my plot of my this particular function. All right, so let us see the second example. Right, so let's say I have another function which is function of gx equals x plus 2 and x square minus 4. All right, so let's try to find out. So first of all I want to find out my domain. Okay, so that is basically very important. So domain means that x square minus 4 cannot be equal to 0. So what I get x square cannot be equal to 4. So x cannot be equals plus minus square root of 2. Sorry, plus minus square root of, actually this is 4. Of 4. So x cannot be equal to plus minus 2. Okay, so basically this is my domain. Okay, x cannot be equal to 2, x cannot be equal to minus 2. All right, so now let's simplify my denominator or numerator. So I have x plus 2, and then in the denominator I have x square minus 4. I can write as 2 square. So the numerator I have x plus 2, and the denominator I have x plus 2 and multiplied by x minus 2. That's how I can write my this. Okay, remember what is my domain in this function. I know that x cannot be equal to plus minus 2. That is the very important conclusion. So now if you notice that from the numerator x plus 2 and from the denominator x plus 2 cancel out each other. So what I am left with, 1 over x minus 2, and what is the criteria or domain, that x cannot be equal to plus minus 2. All right, so this is my function. All right, so let's try to find the vertical asymptote. Guys, remember how I'm going to find vertical asymptote. I need to equate my denominator equal to 0. So to find vertical asymptote, I need to equate the denominator. So my denominator is equal to 0. So what is my denominator? X minus 2. So x equal to 2. So at x equal to 2, I'm going to have a vertical asymptote. So let's try to plot it. So this is my x and this is my y axis. So let me draw a vertical line at x equal to 2. So this is my vertical line at x equal to 2. So this is 2, right? So now if I try to plot 1 over x minus 2, you might notice that this is going to be something like that. And remember, the graph is going to never touch the vertical line, also never cross the vertical line. Now so now I am going to try to plot this domain where it says that my x cannot be plus 2 or x cannot be minus 2. Of course, in nowhere in the graph I have x equal to 2 because it never touch. What about x equal minus 2? So minus 2 is somewhere here. So this is my minus 2. So that means I am going to have a hole in this graph at that location. So if I try to plot that hole, so that in my graph I am going to have a discontinuity. So this is basically finally the plot of my this particular function. So that will be end of this video. In the next video we are going to try to learn horizontal asymptote, and we are going to try to solve a complete problem. Okay, so